presentation. It goes to Jiaxi Jiang. The title is Critical Flux on a Submerged Membrane Bioreactor for Nitrification of Source-Separated Urine. Congratulations, Jiaxi Jiang.
Thank you, Professor, and thank you, CESE 2021.
You're welcome.
Hi everyone, my name is Jiaxi Jiang from University of Technology, Sydney. I'm going to talk about the critical flux on submerged membrane bioreactor for nitrification of salt-separated urine today. So what you can see here is a mineral fertilizer that are widely used for agricultural purpose, but it accounts for 2.5% of global greenhouse gas emissions. The use of nitrogen fertilizer in particular responsible for up to 75% of the total carbon footprint in crop production. Surely we can do better. Let's think about what would be the dream fertilizer for the future. How about sustainable? It could be produced right here at household level under normal temperature and pressure conditions and chemical-free. How about local? So that materials are readily available and free of charge. How about more efficient in road transport and logistics, so that the distribution of fertilizer could be a lot more safer, faster, flexible, and affordable? Thanks to the urine diversion toilets, they make our wishes fulfilled. Yes, we are talking about human urine. Do you know that what we treat as a waste can actually be a liquid gold, contains all nutrients that plants need to grow? In fact, it contains up to 90% of nitrogen, 80% of phosphorus, and 90% of potassium in only 1% of the total wastewater volume. This unique composition makes it, at the same time, a heavy burden for conventional biological sanitation. The MBR in this design is therefore functioning as a stabilizer, oxidizes unstable ammonia into stable nitrate, remove bad smells, and reduce solution pH. To do so, we can achieve a complete nutrient recovery, maintain a balance between supply and demand in natural resources, reduce wastewater treatment plants' operational cost, achieve high effluent quality, replace or reduce the chemical fertilizer usage, save water energy use and greenhouse gas emission, provide household additional incomes and contribute to food security and self-sufficiency in agriculture sector. Like any membrane-assisted technologies, membrane fouling will continue to be a major challenge for the application of MBR in urine nitrification. The membrane fouling can lead to transmembrane pressure increase, decline of permeate quality and membrane performance, increase of membrane operation and maintenance cost, and decrease of membrane module usage lifespan. The concept of critical flux and critical flux for irreversibility in submerged MBR has been proposed to control the membrane fouling and optimize the system treatability. However, no publication has yet investigated the reversibility of membrane fouling in UFMBR fed with hydrolyzed human urine. Most of previous literature evaluated membrane filtration performance in submerged MBR for municipal wastewater or greywater treatment, which has substantially different fouling propensities. As such, an investigation of the critical flux and its reversibility in UFMBR fed with undiluted salt-separated urine was conducted in this study. A lab-scale UFMBR with total effective working volume of 4.5 liter was operated to treat hydrolyzed salt-separated urine. The feed stream constitutes an automatic pH controller and pump. Is designed to achieve a continuous feeding and maintain the pH of sludge mixture at approximately 6.2 during the entire operation period. An air diffuser was placed at the bottom of bioreactor to maintain the dissolved oxygen level in a range between 4.3 and 4.5 mg per liter. UF membrane module with total effective area of 0.02 square meter is used in this study as well. The timely transmembrane pressures were measured by pressure transmitter. An additional set of supported UF membrane module was connected with an automatic water level controller to control the minimum and maximum water level. The impact of free ammonia and free nitrous acid on nitrifying bacterial activity during UFMBR startup and stable operating was studied in this section as well. The first nitrate accumulation occurred within the first 19 days of operation when pH of reactor fluctuated at relatively high range. This implies that the pH change could lead to the FA and FNA inhibition on nitrifying bacterial activity. The specific growth rate of AOB is higher compared to that of NOB growth rate within the discussed pH range, resulting in the accumulation of the nitrite intermediate. The second nitrite accumulation was observed from day 30 to 64 when reactor pH was maintained at the desired pH value. One reason for this observation could be due to the large amount of free ammonia available inside the reactor. The increase of free ammonia to 2.3 mg per liter under ammonia nitrogen shock loading inhibits the NOB activity, resulting in unbalanced growth between NOB and NOB. The UFMBR was capable of adopting 4 strands stored human urine from day 87, and the system was maintained at the desired pH value around 6.2 for stable operation. pH readings always fluctuate after the pH electrode cleaning and calibration, where the nitrification process remains stable. This implies that pH fluctuation can be an indicator that reflects the instability of nitrification to some extent, but free ammonia and free nitric acid concentrations are more useful in order to control inhibitory effects and maintain the system's stability. The study on effects of aeration intensity and sludge concentration on critical flux shows that higher aeration intensity is more favorable for sludge-rich submerged UFMBR to maintain critical flux at certain values and eliminate the degree of membrane falling. For instance, under the same aeration intensity at 0.3 cubic meter per hour, the critical flux for the sludge concentrations at 2, 3.5, and 5 grams per liter are 58, 56, and 51 liter per square meter per hour, respectively. The falling reversibilities at various aeration intensities is studied here as well. At the aeration intensity of 0.1 cubic meter per hour, for instance, the real-time transmembrane pressure values proportionally increased between the first 5 consecutive flux height. The total falling rate remains 0 before flux reaches to 28 liter per square meter per hour. This indicates that the reversible falling was predominantly on the membrane surface at the early stage of improved flux step assessment. The physical cleaning method using intermediate flux of 0.5 liter per square meter per hour is effective in reducing the influence of falling history on membrane. However, an increase in real-time transmembrane pressure was observed from flux step 6, suggesting falling cannot be physically removed by proposed intermittent relaxation cycle. Once imposed flux exceeds 28 liter per square meter per hour, the membrane irreversible falling starts. Furthermore, the incremental irreversible falling rate and total falling rate do not exceed the critical falling rate at all times. This implies that neither critical flux or critical flux for irreversibility was reached among all fluxing stepping. The formation of cake layer on membrane surface remains removable up to a maximum imposed flux of 58 liter per square meter per hour. Similar observation has been found in other 2 sets of aeration intensity at 0.2 cubic meter per hour and 0.4 cubic meter per hour. In summary, the pH fluctuation can be an indicator that reflects the instability of nitrification to some extent, but free ammonia and free nitric acid concentration are more useful in order to control inhibitory effects and maintain the system's stability. Secondly, the influence of falling on membrane can be elevated by intermittent relaxation or moderate aeration intensity. Due to absorption of micromolecular or colloidal organic matter inside membrane pores and formation of polarization layer at adjacent membrane surface, a small amount of irreversible falling was gradually built up on the membrane, despite the membrane filtration operated at subcritical conditions. To operate nitrifying UFMBR on the subcritical rate does not prevent the gradual development of the falling on membrane. The falling mechanism for minor irreversible falling under subcritical condition in our study were pore blocking and polarization. Thank you. Any questions?